graduation days. It's a blacked out haze. I know this cul-de-sac is coming back, 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 back. Who cares if we're obscure? Homecoming serve.
This is the first of 2 lectures where we're going to be focused on Galois groups of polynomials following section 14.6 of Dummett and Foote. And ultimately, the goal is going to be able to take polynomials of low degree, cubic polynomials, quartic polynomials, and say, what is the Galois group of this polynomial? Okay, so what does that mean? Let f of x in f bracket x be separable. The Galois group of the polynomial f of x, denoted gal f, is defined to be the Galois group of E over f, where E is a splitting field for f of x over f. Okay, so in this first lecture, we're going to do a lot of background setup. And in the next lecture, we're going to see lots of applications. So a main idea is going to be to consider the Galois group of this polynomial f as a subgroup of a certain symmetric group. So how does that work? If k over f is Galois, then we know that k is the splitting field of some separable polynomial, little f of x in f bracket x. Okay, so k is the splitting field of this polynomial f of x. K is generated over f by the roots of f of x. So k is f adjoin that finite set of roots. If you have an element of the Galois group of k over f, we know that it permutes the roots of f of x. But in fact, we know something better, that if f of x, maybe it's not irreducible in f bracket x, maybe it factors into a product of a bunch of irreducible factors. So if g of x is an irreducible factor of f of x in this ring, at polynomial ring f bracket x, then this Galois element permutes the roots of g of x in the splitting field. Okay, so just remember, k is the splitting field of this polynomial f of x. Every root of f of x is in k. So if g is an irreducible factor of f of x, the roots of g are contained in the roots of f. Okay, so we know that every Galois element gives a permutation. We also know that these Galois elements are determined by these permutations. So what does that mean? Sigma is determined by this permutation of the roots of f of x because these roots generate k over f. So if I tell you where sigma sends each of the roots of f of this polynomial f of x in k, then because k equals f adjoin these roots, that determines where sigma sends any element of k. Okay, so now what we're going to do is we're just going to fix a labeling of the roots of this polynomial f of x. Let's say alpha 1, alpha 2, up through alpha n. It doesn't matter what labeling we choose. We have these n roots, and we just like list them in some order. We just make a choice, and then we stick with it. Okay, so once we've named these roots, we can say that k is the field generated over f by these roots. So we know that sigma gives a permutation of the roots, alpha 1 through alpha n. So it gives a permutation of these labels of the roots. Like maybe sigma sends alpha 1 to alpha 3. That's like sigma sending 1 to 3. So it gives a permutation of these labels. What are these labels? They are the integers from 1 to n. So every sigma in the Galois group of k over f gives an element of Sn. Okay, this gives us an injective homomorphism from the Galois group to the symmetric group, Sn. So right now what we've seen is that each sigma gets mapped to an element of Sn. And we know that this is injective because sigma is determined by the permutation of the roots. So it's not possible for two different permutations to map to the same, two different Galois elements to map to the same permutation over here. So why is this a homomorphism? This is easy to check, and I recommend that you do this once. Really what's going on is that the group operation on both sides is just composition. Okay, so what does this tell us? It tells us that the Galois group of K over F is isomorphic to a subgroup of the symmetric group Sn. Okay, what is n here? Just to emphasize, where does n come from? There are these n roots of f of x. F of x is separable, so there are n distinct roots, alpha 1 up through alpha n. So n is the degree of this polynomial f. And what is the relationship between k and f? Is we know that k is the splitting field of this polynomial f of x in f bracket x. So what is n here, where we get this subgroup of Sn? It's the degree of this separable polynomial f of x in f bracket x, for which k is the splitting field of f of x over f. Okay, so now you can say, okay, we know that the Galois group is isomorphic to a subgroup of Sn. What else can we say about the subgroups of Sn that arise here? So I'll pause and erase and talk about that question. We know that the Galois group of K over F is isomorphic to a subgroup of the symmetric group Sn. But what else do we know about this subgroup? If f of x is irreducible, then we know that the Galois group of K over F acts transitively on the roots of f of x. So this is a corollary that we proved in lecture 19. So what does that mean? Given alpha I, alpha j, two of these roots, there exists an element sigma in the Galois group of K over F such that sigma of alpha I equals alpha j. So you can always send one element to another element via some Galois element, some sigma. Okay, so what does that mean? If you think about what this means over on the level of permutations of roots and the subgroup of Sn, this means that the Galois group of K over F is isomorphic to a transitive subgroup of Sn. That means it's a group of permutations such that for any I and j between 1 and n, there exists some element of this group that sends I to j. Any element from 1 to n can get sent to any other element by some permutation in this group. Okay, so that's if f of x is irreducible. So what if it's not irreducible? Well, remember, it's still separable, but it does factor into a product of irreducibles that are distinct in f bracket x. Let's say f1 of x times fk of x, where let's say the degree of each fi is ni. And each one of these is irreducible. So what does that mean? The degree on the left is n. The degree on the right is also n. So the sum of these ni's is n. Okay, so we know that each Galois element permutes the roots of f1 and permutes the roots of f2 and permutes the roots of fk. So that means that the Galois group is isomorphic to a subgroup g1 cross g2 cross gk of Sn1 cross Sn2 cross Snk. What's happening is Galois elements are only permuting the roots within each block corresponding to the irreducible polynomials. Okay, so more than that, we can just apply this previous result about what happens when f of x is irreducible to say that the elements of the Galois group of K over F act transitively on the roots of f1 and act transitively on the roots of f2 and so on. So each one of these GIs is a transitive subgroup of Sni. So what we get is when f is reducible, we get this subgroup of this direct product of symmetric groups, and the subgroup that we get within each piece is a transitive subgroup of that symmetric group. Okay, so now we're going to look at some examples. I've written one here, and we'll do another right after this. Let's consider this example we've talked about quite a lot. Q joins square root of 2 and square root of 3 over Q. This is a Galois extension. It's the splitting field of the polynomial x squared minus 2 times x squared minus 3 over Q. This has four roots, square root of 2 minus square root of 2, square root of 3 minus square root of 3. We'll just fix this ordering and stick with it. So I'll think of this being alpha 1, alpha 2, alpha 3, alpha 4. So every permutation of these roots corresponds to a permutation of 1, 2, 3, 4 with this labeling. Okay, so what is this Galois group? It consists of four elements: the identity, sigma, tau, and sigma times tau, where Sigma sends root 2 to minus root 2, root 3 to root 3. Tau sends root 2 to root 2, root 3 to minus root 3. So now the elements of this Galois group correspond to permutations in S4. What permutation do we get from the identity automorphism? The identity element of this Galois group is the identity permutation. It just fixes everything. So it sends root 1 to root 1, root 2 to root 2, root 3 to root 3, root 4 to root 4. Sigma switches the first two roots and leaves the third and fourth fixed. So it corresponds to the permutation 1, 2. Tau fixes the first two roots and switches the third and fourth. So it corresponds to 3, 4. And sigma tau corresponds to 1, 2 times 3, 4. Okay, so over on the right, we have a subgroup of S4. I'll point out that this subgroup of S4 is not transitive. For example, there's no element of this Galois group that sends the first root square root of 2 to the third root square root of 3. There's no permutation here that sends 1 to 3. Okay, well, I mean, that tells us that f of x, x squared minus 2 times x squared minus 3, is not irreducible, right? Because if it were irreducible, this subgroup would have to be transitive. Of course, we already knew that this was not irreducible because it's handed to you as a product of polynomials. So what are we actually getting? Each one of these polynomials is irreducible. So we're seeing that the Galois group is isomorphic to a subgroup G1 cross G2 of S2 cross S2. And this subgroup is isomorphic to S2 cross S2. S2 is a transitive subgroup of S2. S2 is a transitive subgroup of S2. Okay, so what I'll point out now is that there was some choice here in how we labeled the roots. Square root of 2 minus square root of 2, square root of 3 minus square root of 3. We could choose a different ordering, say square root of 2, square root of 3, minus square root of 2, minus square root of 3. And then now sigma would correspond to 1, 3 instead of 1, 2. So we would get a different subgroup of S4, but it would be isomorphic. Okay, so different labelings give different subgroups, but the isomorphism class of the subgroup of Sn that you get does not depend on how you order the roots. Let's consider a next example, something that we've talked about quite a lot already. Q adjoin cube root of 2 and zeta 3 over q. So cube root of 2, think of as the positive real number that cubes to 2. And zeta 3 you can think of as e to the 2 pi I over 3. Negative 1 plus square root of minus 3 over 2. Okay. So this is a Galois extension. It's the splitting field of the polynomial x cubed minus 2 over q. What are the roots? Cube root of 2, zeta 3 times cube root of 2, and zeta 3 squared times cube root of 2. We have seen that the Galois group is isomorphic to S3, and that it's generated by these two particular automorphisms of this field fixing q. Sigma, which sends cube root of 2 to zeta 3 times cube root of 2. So it sends the first of our roots of our irreducible polynomial to the next one. And zeta 3 to zeta 3. And tau, which sends cube root of 2 to itself and zeta 3 to zeta 3 squared. So you can see, what does this do to the roots? Well, it sends the first root to the first root, but it sends the second root to the third root. And think about what it does to the third root. It sends zeta 3 squared to zeta 3 to the fourth, which is zeta 3 to the first. So it sends the third root to the second one. So we can see these Galois elements correspond to permutations in S3, permutations of the labels of these three roots. So we've just chosen an order and we stick with it. Sigma sends root 1 to root 2, root 2 to root 3, and root 3 back to root 1. So it corresponds to the permutation 1 goes to 2 goes to 3. Tau fixes the first root and sends 2 to 3 and 3 to 2. And now I said that the Galois group is isomorphic to S3 generated by these two elements. These two permutations generate S3. Okay. So what are we going to do in this lecture and the next? We know that every finite group is isomorphic to a subgroup of Sn. Right? This was Cayley's theorem that we proved in Math 206a. And we know now that you can think of Galois groups as subgroups of Sn. So every finite group is isomorphic to a subgroup of Sn. Every Galois group of a polynomial is isomorphic to a subgroup of Sn. Which subgroups of Sn do you get? So which finite groups occur as the Galois group of k over q for some Galois extension k over q? Well, this just is the inverse Galois problem over q that we briefly mentioned in lecture 25 on cyclotomic polynomials. One thing that we didn't give the full proof, but in section 14.5 of Dummett and Foote, using what we know about Galois groups of cyclotomic fields and Galois groups of composites of Galois extensions, using one additional input about the existence of primes in certain residue classes, you can show that every finite abelian group does occur as the Galois group of some Galois extension of Q. In section 14.6, the focus of this lecture and the next one big goal is to show that for when n is small, we can very explicitly understand which subgroups of Sn arise. So every subgroup of S4 does arise as the Galois group of some Galois extension over Q. And a big goal for this lecture and the next one is we're going to take a polynomial f of x and f bracket x that we want to be separable, and we want the degree to be at most 4. For various technical reasons that'll make it easier to work out what's going on, we'll assume for most of the time that the characteristic of f is not 2 or 3. So we're going to let E be the splitting field for f of x over f. And what we want to do is give a procedure to compute the Galois group of this polynomial f, which is the Galois group of E over f. Okay, so what is this going to do for us? This is going to enable us to answer lots of questions with specific examples. So here's an example that was Algebra Qualifying Exam Fall 2010, number 5. Find the Galois group of the cubic polynomial x to the 4th plus 4x plus 2 over q as an abstract group. Okay, so you can check pretty easily that this polynomial is irreducible. So it's separable. It's an irreducible polynomial over a field of characteristic 0. So the Galois group is going to be isomorphic to some subgroup of S3. But which one is it? Okay, so what we're going to do in this lecture is now we're going to spend some time talking about symmetric functions and the Galois group of certain function field extensions. The main thing that we're going to get out of this is we'll talk about the discriminant of a polynomial and what it tells you about its Galois group. So that'll be a big focus of this lecture. And in the next lecture, we'll solve this specific problem. And we'll also talk much more generally about Galois groups of polynomials of low degree.